Hello, everyone. The history of the approximation of pi is very rich and very long, spanning over 2,000 years of mathematical history, and to cover all of it within one video would effectively be impossible. However, this video will show the difference between antiquity, what was done in antiquity, how it was approximated then, and an introduction to the modern methods of how it's done. And so the first one will be the method of exhaustion used by the ancient Greeks. And then the more algebraic, more modern Taylor series. It's how we use higher mathematics in order to make things just so much easier for us. And I mean, there are definitely a lot of ways. If you want to talk about the applications of mathematics to engineering, physics, natural sciences, that would be very, very easy. But I believe it's almost equally as powerful to show just how useful it is really just for calculating the value of pi. I think that is also a very beautiful way of doing it. And this is what we'll be doing today. But without further ado, we're going to look at the method of exhaustion. So what the method of exhaustion does is take regular polygons that are inscribed or drawn inside of a circle and increase the number of sides. And so what you're going to see, although these aren't perfect drawings, what you're going to see is that the difference in the area gets smaller and smaller and smaller. And so you would presume that as the number of sides goes off to infinity, the area of the polygon is going to approach the area of the circle. And so you can see this for the case 3, n equals 4, size equals 5, hexagon. And so what we're going to look at is the general case. We're going to see why this actually converges. And so here, although this isn't a very good drawing, what you do see is a general case. So if you look at this, you have a polygon that will have a regular polygon with n sides. And so what you can do is going from the center of the circle, you can draw lines to each of the vertices, and between two adjacent lines, or well, I mean, all of them are adjacent, but between two consecutive lines, I suppose, because you have the circle is radians 2 pi. One trip is 2 pi. Here, what you have is, for this angle over here, it's going to be, there are going to be n of those. They'll make 2 pi, so it's 2 pi over n. So that's relatively straightforward, but we're going to use this to end up seeing what the value is going to converge to. So we have already established that the area of the regular polygon is just going to be the sum of these n triangles. And so we're going to look at each of these triangles individually. So if we look at this triangle, what it's going to have is an angle of theta between two sides, which are equal to the radius of the circle. And so we're going to look at the area of the triangle because of the fact that we know that if a triangle has two sides, A and B, and the angle between them is theta, the area of that triangle is going to be 1/2 AB times sine theta. So in this case, A equals R, B equals R. And so we get the area of the triangle is 1/2 R squared sine theta. We already established theta is 2 pi over n, so R squared equals sine 2 pi over n, all over 2. The area of the polygon, the regular polygon, is just n times the area of each triangle. So it's n R squared sine 2 pi over n, all over 2. So we're going to show that this actually converges. So what we have here is we're going to look at the limit of this expression. And what's very interesting, and we're going to use a little bit of an algebraic trick. Technically, n is equal to 1 over 1 over n. And so this is going to be very, very useful. And we're going to see why. What happens here is we have R squared sine 2 pi over n, 2 over n. Let's look at the numerator. So the angle is essentially going to 0 and sine of 0 is 0. So the top is going to 0. 2 over n, well, as n goes to infinity, that's just going to go to 0. So what we have here is a case where it's indeterminate, and you can use L'Hopital's rule. So in the denominator, it's very simple. Just use the power rule, and you get the expression there on the bottom. But for the top, what you're going to do is use the chain rule. So it's the derivative of You're gonna get the derivative of sine 2 pi n with respect to 2 pi n. So it's gonna be cosine 2 pi n multiplied by the derivative of 2 pi over n with respect to n, getting negative 2 pi n squared. The limit of this, and if you just clear the algebra, you're gonna get the limit of pi r squared cosine 2 pi n. As n goes to infinity, the angle goes to 0, so cosine of that is just gonna go to 1, and so you get pi r squared. So what we're looking here is, initially we're going to look at this. If we take the unit circle, it is going to have an area of pi. And if we look at the upper quadrant, it's going to have a pi. If we put it on the Cartesian plane, the x and y axis, put it look at the first quadrant, it's going to have an area of pi over 4. And so if you look at if it's at a coordinate x, y, or whatever, then by the Pythagorean theorem, x squared plus y squared is going to equal 1. Y is going to equal the square root of 1 minus x squared. And so the thing is, if you take the area under this curve, or basically just take the integral, the height, y, you'll get that pi over 4 equals the integral from 0 to 1 square root of 1 minus x squared dx. Now, the question here is there any real way you can solve this? And the answer is yes. We're going to use something called the Taylor series. And although this is not a really in-depth explanation of what it is or how it works, basically what it does is you take a function and you try to approximate as a polynomial by ensuring that at a certain point it has all the exact same derivatives. So here, you can verify this using the power rule, just that, at the value a, it's going to have a first derivative that is equal to the first derivative of f at a. At, the second derivative is going to be the same at a, third, fourth, and also the first one, because you just plug in, n equals 0, you have, n factorial is 1, x minus a to the 0 is going to be 1, and, f0 of a, that's just going to be the value of f at a. And the Maclaurin series is just where a is equal to 0, and that's what we're going to look at. So let's look at 1 plus x to the 1/2. So if you look at this thing, the first value it's going to have is 1. And so that's going to be the first term of this series, 1. Now, look at the next series. If you take the derivative the first time, you're going to get 1/2. The exponent is going to be negative 1/2 at that point. So if you take the derivative again, it's going to be negative 1/2. You're multiplying negative 1/2. And then you're going to have a negative 3/2 as your exponent. And then then negative 5/2 and so on. And so what you're looking at here is just the product. This product, technically you can verify this. This will give you the value of the derivative at that point. And so now let's look at, what if we just plug in negative x squared for x? And so what's going to happen is it's going to be negative x to the power of n, negative x squared to the power of n, which is negative 1 to the power of n times x to the 2n. So this is the explanation for UF here. Also, we did a little bit of a rearrangement. So you have a pi product here. You're multiplying, because if you look at the top here, it's just 3 minus 2n. Here it's going from j equals I to n. You're just keeping track of that product. And each time you're multiplying in the denominator by 2, so you just put 2n in the bottom here. So now we have our little function here. And this does actually converge. That's beyond the depth of what we're doing here, but it does converge. That's all you really need to know. So anyway, we're looking at pi equals 4, because we're taking this expression here. Pi is going to be 4 times the integral of 0 to 1 of square root of 1 minus x squared dx. Plug in the value here. You use the power rule, and then you're evaluating this definite integral. So you did the power rule here. You get 2n plus 1 in the denominator. And then you just plug in 1 and 0, and you get this value over here. And that is really all you need to know. Hopefully this video was at least a nice introduction. If not, that's unfortunate. But I'll see you guys later.